In this video, we're going to take some of the theoretical concepts that we've been learning about in the last few sections, specifically additive secret sharing and fixed precision representation, and show how you can leverage PySyft to do this in sort of an easy and intuitive way, right? Where it just feels like you're using normal PyTorch tensors, even though they're being encoded in this way under the hood. The first thing I'd like for us to do is clear out the objects that are inside of Bob, Alice, and Secure Worker. We're going to use these as our sort of example workers to share things on. And then we want to create a little bit of data. So do our standard 1, 2, 3, 4, 5 tensor. Looks good. And now I'm going to show you this next method called share. Now we can pass in a series of workers here, arbitrary number. We could do 2, 3, or 20. And what this will do is actually split this x value into multiple different additive secret shares, and then send those shares to Bob, Alice, and Secure Worker, such that we will have pointers to that data. So let me show you what I mean. So when we call .share, what it did under the hood is generated 3 different pointers to the 3 different shares that we had sent to Bob, Alice, and Secure Worker. And so now if we actually take a look at, say, one of these shares, we can see it is a bunch of sort of large random numbers. However, the nice thing about this is that we can actually, again, just like we did with regular pointer tensors, just pretend that it's another tensor. And as you can see, it's create another share on Bob's machine, create another share on all 3 of these guys, so Bob, Alice, and Secure Worker. And y is another additively shared tensor. And then if we call y.get, it decrypts this encrypted tensor and gives us back the result of our computation, the result of our addition, 2, 4, 6, 8, 10. Now, however, we did mention before that these are integers, right? So we're doing integer computation here, whereas in the context of federated learning, we want to be able to do this on decimal valued numbers. So this is where PySyft also adds in a bit of extra functionality. So let's say we have our canonical tensor again, but this time we're going to say, actually no, let's do decimal values. So 0.1, 0.2, 0.3, 0.4, 0.5. Cool. And now we're going to encode this using fixed precision. And x is now a fixed precision number. Under the hood, inside of x, are the values 100, 200, 300, 400, and 500. However, this is still getting interpreted, and all the mathematical operations are such that if we were to go back to a regular encoding, it would still look like this 0.1, 0.2, 0.3, 0.4. So if I go to x dot float precision, oh, excuse me. As you can see, it restores the original values. Now, you might find this to be an interesting representation, and this actually alludes to a little bit of how PySyft works under the hood. So this is actually a tensor chain. At the top, we have sort of a dummy PyTorch wrapper. There are reasons why we have to do this to make it compatible with the rest of the PyTorch ecosystem. This forwards all commands to its child. So basically x.child. So let me just show you this here. I'll create another fixed precision tensor. So the type of x is a torch tensor. The type of x.child is a fixed precision tensor, and the type of x.child.child, that you can see where this is going, is another native tensor, right? So this native tensor is actually the raw data. This is the actual encoding of this 100, 200, 300, 400, and 500. This is what we call an interpreter, right? So whenever you execute a command, it gets called on this wrapper on the top, which then passes it off to .child automatically. It will always pass it off to .child. .child says, okay, you're trying to, say, add 2 tensors together. Well, since I am a fixed precision interpreter, I know how to add this appropriately given the fact that the underlying data is encoded in a particular way. And this is how it knows how to do the appropriate operations on this sort of specially encoded data. which it then calls on .child, which actually manipulates the data. So as it turns out, pointers actually work this way too, right? So pointer is a special type that when the wrapper calls the pointer knows how to handle sort of the remote encoding of this particular data. So that's just a little bit on how sort of PySyft tensors work in a bit more advanced way, and like why what this print statement is really saying. Like it's sort of saying we have a wrapper, and this little caret says is sort of a .child signal. So this is the child of the wrapper, and then this actual data is a child of the fixed precision tensor. So there you go. And of course we can go y equals x plus x. Y is still a fixed precision tensor. Y dot float precision. And there you go. We have the result of our computation. And as you might expect, we can actually use these together. So if I said x equals th dot tensor 0.1, 0.2, 0.3, and I said fix precision and share with Bob, Alice, and secure worker, y equals, so I have x. So as you can see, this is the nesting, right? So at the top we have the wrapper. This goes to a fixed precision tensor, which says, okay, interpret everything beneath me as if it's, you know, actually a decimal, but I know that it's going to be encoded as an integer. Its child is an additive sharing tensor, which knows how to encode integers, right? So as you remember here, the child of the fixed precision tensor always has to be an integer tensor, because the whole point is to be able to store sort of a theoretically decimal value number as an integer under the hood. And since additive secret sharing knows how to deal with integers, it then has these pointers to Bob, Alice, and secure worker, right? And so I can go y equals x plus x. Y also ends up being a fixed precision tensor wrapping an additive sharing tensor. And I can call y equals y dot get dot float precision. And now we have the result of our computation. So I hope you really see that the power that PySyft is able to give you, these multiple layers of interpretation, of abstraction, and of message forwarding to remote machines. In the next section, we're going to talk about the next project that you want to be able to use these kinds of tools for. So I'll see you then.